So multiple choice questions, any question that just calls for a simple answer without submitting any work. Desmos is your best friend when it comes to that, right? Any graphing technology would be your best friend, right? So for number one, it says which of the following are the x-intercepts for the function f of x is equal to 2x cubed plus x squared minus 2x minus 1. All right. The power, the high power in the function, or the degree of the function, dictates how many distinct roots there should be, or how many roots there should be in total. Some of them could be imaginary, though. We're going to be careful. But if you see 3 distinct roots on your graph, then that's all you need. Right? So it's just the x values that I care about. And those x values are -1, -1/2, or -0.5 if you want, and a +1.
Professor?
Yeah.
Are these the exact type of questions that you'll be asking on the final?
No, they could vary from this. I mean, they could be.
I mean, like I'm not saying word for word, but like the type of problem.
No, I mean, it's going to be an x-intercept question, but it may not be a multiple choice.
Okay.
All right. So -1, -1/2, and +1. All right. So that's all you would need to do. All right. So even if a question required you to show work, the work could be the graph. All right. So just draw a quick sketch of the graph and include that, or submit a Desmos link of the graph. The thing is, if you're doing a Desmos link for the graph, remember, if I tap on this, it's not going to show me any of those solutions. You know, if I tap on it again, they'll come up. But when I share this, it's not going to translate. So you can do a screenshot of your Desmos work, or you could just type in your x-intercepts, right? So -1, 0. You know, just do it that way. Oops, that's not what I wanted to do. -1/2, 0. Just turn on the label so it shows up on the graph. Now this one's multiple choice, so you wouldn't have to do any of this, but if it's a free response type question, you would want to have this level of detail. All right. Number 2 is more involved, but it's stuff that all of this is stuff that we've seen before. It's just a question of how fresh it is. Find the slope of the secant in terms of a and x. All right. So the general rule that we're following here is f of a plus, well, there's a couple of different variations of this. We'll use this one, f of x minus f of a. It's a little easier, over x minus a. Because there's one where it's f of x plus a, but this one's a little bit nicer. All right. So f of a would be 2a cubed plus 5. All we're doing there is replacing the x in the original function with an a. All right. So f of x is equal to 2x cubed plus 5. F of a is equal to 2a cubed plus 5, all over x minus a. Distribute. Simplify, combining like terms, all that good stuff. Yeah, I have a common, or like terms anyway. 5 and -5 would cancel. And that would give me up top 2x cubed minus 2a cubed over x plus, or x minus a. So then the directions here doesn't say to simplify, but they could. So we might as well just go the distance. I have a common factor of 2 that could be pulled out. Now the top is factorable. All right, so a factoring rule, difference of 2 cubes. Different forms of it, but I'll write it as a cubed minus b cubed is equal to a minus b times a squared plus ab plus b squared. All right, so that's difference of 2 cubes, the rule for it. So everywhere I have an a, I'm going to swap it out for an x. Everywhere I have a b, I'm going to swap it out for an a. So the expansion here, 2 times x minus a, x squared plus xa plus b squared, all over x minus a. Oh, b squared. Geez. A squared is what I meant to write. All right, and then I have that common factor of x minus a that would cancel away. And we would just be left with 2 parentheses x squared plus xa plus a squared. And so that would be the simplified form of the difference quotient in terms of a and x.
Can you just scroll up for a second so I can see the difference of the cube? Yeah, thank you.
No problem. Now, number 3 is just talking about notation dealing with increasing, decreasing, constant, and stuff like that at any points of discontinuity for a particular graph. Right. So the domain is the start and the stop. So where does the graph start? It starts over here. Where does it stop? It stops over here in terms of x. Domain is always related to the x, right? But there is a break in the graph, right? So it really, yeah, it goes from -4 to 4, but it has a kind of a layover in Dallas here. You know, you got to stop at 2, all right? So my domain would be going from -4 to 2. Brackets include a point, parentheses exclude. So if there's a solid point, it corresponds with a bracket. If it's an open circle, it corresponds with parentheses. All right, so that's one piece. That gets us through this path here. All right, but then the rest of the way would be going from 2 to 4. And because we're piecing these two intervals together, we connect using a U for union. All right. Go with a blue. So the next part is asking where the function's increasing. Increasing as a positive slope, so it's going uphill. That would be this piece. All right, that's happening from the x value of -4 to the x value of 0. Decreasing would be where it's going downhill. So that would be going from 0 to 2. All solid points. Oh wait, actually at 2, it's not a solid point, it's an open circle. All right, so 0 to 2, parentheses on the 2. Constant would be wherever it flatlines or goes horizontal. Let's go with orangey color here, otherwise known as orange. All right, so it flatlines from 2 to 4, but there's an open circle at 2. That gets parentheses, 4 is a solid point. And then the points of discontinuity, that would be wherever there's a break in the graph. And that only happens when x is equal to 2. A function being even, odd, or neither, well, or an equation, in this case, is an equation. Even is symmetric over the y-axis. Odd is symmetric through the origin. That's all a fancy way of saying graph it and take a look at the picture, see what's going on. All right, so x squared over 4 minus y squared equals 1. Just turn off these labels for a sec. All right. Do a little zoom out just so I can see the picture. All right, so this does look like it has y-axis symmetry. All right, so this is an even, this is y-axis symmetry. All right. So it's even because it has y-axis symmetry. Number 5 is asking for horizontal and vertical asymptotes. So create the graph. If you could pick it up from the graph, then you're in good shape. If you can't, then you do it algebraically, but the hope is that you can pick it up from the graph. All right. So this one's kind of a funky looking graph, but I definitely see some vertical asymptotes. All right. It looks like it's going vertical in a couple of different places. All right. But picking out the vertical asymptote is kind of tricky in this case, but the horizontal asymptote, the horizontal line that it's approaching, that seems to be the x-axis. All right, so it's pretty safe bet that the horizontal asymptote is the x-axis, but we'll verify that too algebraically in a second. All right, but for the vertical asymptote, in every case, you factor everything. All right, so this would be factor and simplify if you can. For the vertical asymptote, we're going to set that denominator equal to 0 after we've simplified the function. It's already simplified. There's no way to go from there. There's nothing to cancel. So I would set my factors equal to 0. and solve. All right, so I'd have vertical asymptote at x equals 0 and x equals -1. All right, and you could verify that visually. X equals 0, x equals -1. That's not a -1. -1. It does look like the red is approaching the green. It does look like the blue is approaching the green. All right. Sorry, the red is approaching the blue. You got it right eventually. So red's approaching the green, red's approaching the blue. And those are the vertical lines on both sides here. All right, now for the horizontal asymptotes, if it's a function, there's only going to be at most 2, really, but we're only dealing with the case where there's 1. Right, so what we do is we find the end behavior model. And the end behavior model we get by taking the term with the highest power on the top of the fraction and dividing it by the term with the highest power on the bottom of the fraction. So y is equal to x over x squared, which would be 1 over x. That's the end behavior model. All right, we'll come back to that again for another problem down the line. I think it's like question 8, but it's an important one. All right. Now, to find the horizontal asymptote from this, what we can do is, well, there's a couple of ways to do it without getting into the concept of a limit. What we would really be saying is, what would this value be if x were to increase without bound, right? So what we would do is replace x with, I'll say infinity, but really it's some very large number. Right. There's other approaches for finding horizontal asymptotes, but this method is going to help you more for calculus. Right. So let me just pop in that value, y equals, for that equation, y equals 1 over x. If I put in some really large number for x, like 100, 1,000, 10,000, and so on, just keep getting bigger and bigger and bigger, I want to be thinking about what the overall value of the function is approaching, right? Visually, I can show you, if I have the x value being equal to 1, it's a horizontal line 1 unit above the x-axis. If I make it 1/10, and so if I make the x value 10, then it's a horizontal line 1/10 of a unit above the x-axis. If I make it 100, it's 1/100th of a unit above the x-axis. You really have to zoom in to see it. But it's pretty clear that the bigger I make the denominator, the closer this horizontal line is getting to the x-axis, right? And so that would make this value, if we could get infinity in there, so this would be y equals 1 over infinity. 1 over infinity would be equal to 0. And so that's my horizontal asymptote. All right. But like I said before, most of the time you can just pick it out of the picture. So there's really no need to really get into this technique, but it's something that is useful going forward. So it was worth talking about a little bit. All right. Trig identity. The trig identity, remember, impenetrable barrier. One should seem pretty familiar. You look at one side, you look at the other side, and then you decide which way you want to go. Do I want to start with the left or start with the right? I'm just trying to remember if this is the one that had the typo in it on the test. I think so. Yeah. This was supposed to be a cosine up top. So there's another typo for somebody. Fixed it on the test, but I didn't fix it on the practice final. All right, that's what the problem should have been. All right. So I'm going to start on the right-hand side because I see that cosecant there. Cosecant 2x is the same as saying 1 over sine of 2x. So I have the sine of x there, but then I also have a 1 over sine of 2x. All right. Sine of 2x, that's an identity. That's the double angle identity. So this would be the same as saying cosine of x over sine of x times 1 over 2 sine x cosine x. All right, so that's one of those identities. So cosine x over sine x over 2 sine x cosine x. All right, we would then do a little keep change flip, unless you wanted to go switch over to the other side, which is also an option. Try to get the two sides to sort of meet in the middle. Nothing wrong with that. All right, but I'm going to use keep change flip. So cosine x times, and so instead of divided by sine x over 2 sine x cosine x, it's going to be times 2 sine x cosine x over sine. Right? That cosine over sine, that's cotangent. So we have cotangent x times 2 sine x cosine x. If I want to move that cotangent to the bottom of a fraction, I would just apply the reciprocal. Right? So this would become 2 sine x cosine x over tangent of x. And that's what we needed. Right? So these identities can be easier or trickier depending on the strategy that you use. If you limit yourself to just working on one side of an equation, you know, of an identity, it can be trickier than it might need to be. You know, but if you do the two sides independently and sort of meet in the middle, then it gets a lot easier. Number 7. Number 7 is a nice easy one. You do this graphically. In fact, that's the approach we should take. If you do a Desmos solution for something like this, it's just like that one with the x-intercepts. If you just create the graph and submit that as your answer, you haven't really told me anything in terms of a justification, right? But if you label up that graph and then state what your appropriate final answer is, then now we're talking. You know? So p of x is equal to 18 times the sine of pi over 6 times x plus 72. All right, nothing shows up on the graph, but that makes sense. I mean, the value is 72, so that's substantial. Make sure you're in the right mode. The mode should be radian. All right, the default setting is radian, so we're good there. What is the maximum and minimum temperatures over the course of 1 year? All right, so x is in months. So I would truncate my graph by restricting the domain. So 0, less than or equal to x less than or equal to 12. And only look at that piece. Now, personally, I would be submitting this as a separate Desmos from all the other stuff. It's just I don't want to wipe out everything, so I'm just kind of leaving it. But I'm looking at this point as the maximum, 390, and this point as the minimum, 954. So I plot those, 390. $9.54. Right. It's asking what the maximum minimum temperature is, or R. So maximum temperature, 90 degrees Fahrenheit, not OP, right? 90 degrees. We'll just say degrees F, all right, just so we have something there. The minimum temperature, (54 degrees Fahrenheit). So now we have a well-labeled graph that justifies our answer. All right. And let me just get this into the document here. All right. Then number 8, state the end behavior model. We went over that before. Very simple. You take the term with the highest power on the top, divide it by the term with the highest power on the bottom. So my end behavior model would be y equals 4x to the 4th over 2x to the 3rd, which would simplify down to just a 2x, y equals 2x. All right. You can check your end behavior model pretty easily just by graphing the original function and graphing the end behavior model. All right. They should behave the same way for extreme values of x. All right. So there's my original function, pretty crazy looking. And here's my end behavior model. As x gets larger and larger, this green graph, or smaller and smaller, if it goes out to the left, goes out to the right, it should behave more and more like this function. Right? It should behave like this for large values of x in the negative or positive direction. Right? And so you can see it appears to go linear after a certain value for x. Right? So now in the middle around 0, they're wildly different, but for extreme values of x, they're very much the same. Right? In fact, it's almost indistinguishable from one another. And you'd really have to zoom in order to see that they can be distinguished from one another. All right. Now, number 9 is, well, any of the law of sines, cosines questions should actually be considered, I don't want to be dramatic, but they're kind of gifts at this point. Right? It's just people tend to make them more complicated than they need to be. Let me just bring it up here real quick. All right, so if you go into Blackboard, under calculators, you see a bunch of different possibilities for Unit 3 under the Unit 3 calculators for law of sines and cosines. I mean, if you can identify what's going on with the graph, I'm sorry, with the diagram, that'll dictate which of the law of sines, cosines calculators you use. So you take a look at what information is given to you. And this information is an angle, a side, and an angle in that order. So this is an ASA. So what I would do is I'd go to Blackboard under Unit 3 and choose the law of sines or cosines calculator that involves an ASA. All right. So I'll bring it up here. Law of sines ASA. All right. The Desmos is your work. All right. So the Desmos calculator is your work. You don't need to really do anything more than that. All right. So I got a little picture here. It's all kind of set up and ready to rock. It's a little out of whack from the diagram that's on paper, though. So you just got to be careful about that, because the angle, side, and angle that are given here are A, B. So angle A, angle B, and side C. Right. So on Desmos, we would treat this would be angle A.
Professor, is the calculator already in degree mode?
Yes.
Okay.
All right. So this would be our angle A in Desmos, just based off the orientation of this triangle compared to the triangle that we have in the Desmos. This would be the angle B on Desmos. And this would be side C on Desmos. So angle A, 52.2, kind of hard to get there. So I'll just type it in. The B I would put at 57, that I can slide to, but it always just kind of comes off. So I might end up typing it in anyway. I got it. And then 4.4 for that C. All right. So this would be angle C on Desmos. So when they're asking for angle B, they're saying find angle B. We would look at C on Desmos, which would be 70.8. That being said, shouldn't really need Desmos for that part of it. The three angles in a triangle add to 180. Subtract the two angles you have from 180 and you'll have your answer. All right. So 70.8, one way or another. And then side C is the one that we would want. Actually, based off of the orientation, C would be this angle here, which is the B. So I'd be looking down for B, which would be 3.9. So if we just label up the triangle based off of the way it's structured in Desmos, they would give us about 3.7 for this side, 3.9 for this side. Comparing it to what we have on paper, I would need this side. Okay. So basically, I mean, long story short, it's just a matter of matching up the diagram that you have on paper with the diagram on Desmos. And what a lot of people will do is just kind of scribble out all the sides and angles, like the labels for the one on paper, and just put in the ones from Desmos, and then later on just figure out what needs to go where.
Professor, could you go over the sides and angles again? Just
The sides and
a quick
angles.
recap, just of the labels.
Like how I know which one's angle A?
No, just like which A, B, C, just a quick, because it looks very like combobulated together.
I'm having a hard time understanding what you're asking.
Just
Like
like
how to-
yeah, just going over the answers. A is blank, you know.
Side A is 3.7. So like that, that's what you want?
Yeah.
Yeah, side A is 3.7. Side B is 3.9. Right, but that's on Desmos. So that would correspond. So the side B, let me just get this diagram in here. All right, so this is the one on Desmos. They're telling us, off the screen there. They're telling us that this side is 3.7. This side is 3.9. We already knew that this one was 57 degrees. We already knew that this one was 52.2 degrees. And this one would be 70.8 degrees. All right, and so this one we were given is 4.4. So it's just a matter of matching that up with the triangle that they gave us on paper. All right.
Okay.
So yeah,
Thank you.
no problem. And so the last one, let me just move this up. Last one's the same idea in the sense that you have a Desmos calculator that's going to do it for you. I mean, you're welcome to do it by hand using the techniques that we covered. It's not really overly difficult to do by hand, but if there's a Desmos calculator that'll do the work for you, then why not just use that? I mean, so you just have to get the information in. Your H and K values are 0, 0. Your A and B values would be 3 and 4. The idea is that we're matching the equation they give us, the x minus h squared over a squared plus y minus b squared, k squared, sorry, over b squared equals 1. So the h would have to be 0, the k would have to be 0, the a would have to be 3, the b would have to be 4. Once you have that, then everything here is presented for you. And in fact, probably a little too much information, because the only thing we would need to know is whether it's a vertical major axis or a horizontal major axis. All right, this one's going to be a vertical major axis. And that's because the y denominator is greater than the x denominator. All right, so I would go down to the bottom of the applet here and just turn off horizontal major, turn on vertical major, and every point that you see here is a relevant point. All right, so I'd have my center. Didn't really need Desmos for that, but 0, 0. The vertices, we have negative 3, 0. We have positive 3, 0. You got 0, negative 4. You got 0, positive 4. And if you go down, you go up. And then for your foci, as long as you determine the type of major axis, vertical or horizontal, that'll get plotted for you. So 0, 2.646 and 0, negative 2.646. All right, and so that was question 10. And that's the final exam. So if you studied this and you have good notes, then you should be in pretty good shape. All right, so stop that.